In continue of our discussion on Norton and equivalent circuits, today I'm going to solve some more examples to show how do we calculate the Thevenin and Norton equivalent of electrical circuits. Here is one example for finding equivalent Norton and Thevenin circuits. Part A, once we find Thevenin and Norton equivalent, that the load Z sub L sees. Part B, design load ZL so that 10 with the angle of -90 degree volt are delivered across it. Okay, so first we want to find Norton and Thevenin equivalent, and then determine the value of ZL so that the voltage across it be 10 with the angle of -90 volt. Okay, here is the circuit. We have a voltage source 50 volt with the angle 0, 1000 ohms resistor at the top. Then we have a capacitor negative J 1000 ohm. We have an inductor J 1000 ohm. And here is ZL. Okay. The first thing we do is finding Z Thevenin. In order to find Z Thevenin, so part A, finding Z Thevenin, we need to turn off the voltage source and look to the circuit from the load. So from here, Z Thevenin. Okay, so from this point we should look to the circuit. So we should notice that ZL is not part of the Z Thevenin. So we look from points A and B. Okay, Z Thevenin. Let's draw the circuit with the turned off voltage source. So we have a 1000 ohm resistor, negative J 1000 capacitor, and J 1000 inductor, and we want to find the Z Thevenin from this point. So Z Thevenin, of course, Z Thevenin is equal to these two in parallel in series with this inductor. So Z Thevenin is equal to 1000 in parallel with negative J 1000 plus J 1000. If we calculate this value, Z Thevenin will be equal to 500 plus J 500, which is equal to 707 with the angle of 45. Of course, we all know how to calculate this value. So we multiply this one with this one and then divide it by the total. So it is like a fraction with two rectangular numbers. we convert these rectangular numbers to polar form and then divide them and then convert back to rectangular and add it with this number. Okay, so Z Thevenin is 500 plus J 500 ohms. Now let's find V Thevenin. In order to find the V Thevenin, we need to draw the circuit again. So here is the circuit. We have all components, 50 with angle 0, 1000, negative J 1000 and J 1000. Okay, we want to find V Thevenin at this point, plus minus V Thevenin. Okay, let's go back to Z Thevenin for a second. For the Z Thevenin, because we look to the circuit from this point and we find the Z Thevenin, all these values were included in like calculation. But here, first thing we should notice, it's like we want to find to see what is the voltage across V Thevenin, because we see that this inductor has an open terminal. The current moving through this inductor is 0. Okay, and so the voltage drop across this inductor is 0. So we can say that both sides of the inductor have the same voltage, which is called V Thevenin. So we can simply ignore this inductor and consider this part of the circuit and find the voltage across the resistor, which is equal to V Thevenin. Why we didn't like remove in inductor in calculating Z Thevenin? Because for calculating the Z Thevenin, we like use these two. We look to the circuit from these 2 points, and we only find the equivalent impedances. We don't care about any current. We want to find impedance. So all of these parts are included in the impedance. But here, because we want to see the voltage depends to the amount of the current moving through the elements. Because there is no current moving through this element, of course this element is off the circuit. So we need to find V Thevenin, which is a voltage across the resistor, capacitor. The easiest way, of course, we can write a KVL here, but there is an easier way, which is voltage division. So we can say voltage across the resistor, which is equal to VCL, which is equal to voltage, Thevenin voltage is equal to the impedance of the in the capacitor over the total impedances, 1000 minus J 1000 times the total voltage, which is equal to 35.35 with the angle of negative 45 degrees. Okay, so this one is the V Thevenin for this circuit. Now that we got both Z Thevenin and V Thevenin, we can simply show the Thevenin equivalent. So Thevenin equivalent will be a voltage source and Z Thevenin. This one is Thevenin equivalent, which is connected to ZL. V Thevenin is equal to 35.35 with the angle of negative 45. Z Thevenin is 500 plus J 500. Okay, And of course, I Thevenin is here, so we put current source Z, not I Thevenin, Norton equivalent. The Norton equivalent is the current source with the Z Norton, which is equal to Z Thevenin, which is connected to the load, which is ZL. Z Norton is equal to Z Thevenin, as we know, and I Norton is equal to V Thevenin over Z Thevenin, which is equal to 0.05 with the angle of negative 90. Okay, now that we got Thevenin and Norton equivalent, let's look to part B of the problem. Part B of the problem says design load so that the voltage of 10 with the angle of negative 90 are across the load. So here, if we say we have this equivalent circuit, we want to have the voltage here VZL equal to 10 with the angle of negative 90. Okay, so how we can do that? It's easy. If we consider this circuit, we see that we have two elements and a voltage source. So we can simply write the voltage division. So we can say the voltage across load is equal to the value of load over the total impedances divided by times by V Thevenin. So let's do that. We can say part B, we can say VL. We know that VL is equal to 10 with the angle of negative 90. Okay, and ZL is a complex value. Let's say it consists of two values, RL plus JXL, because we have no idea what is inside the ZL. ZL can be like a single resistor, or the combination of resistor and inductor, or resistor and capacitor. So let's continue. We can say the voltage across the load is equal to Z load over Z load plus Z Thevenin times V Thevenin. So this one is a voltage division. Let's just substitute the values. VL, we want to have the value of 10 with the angle of negative 90 is equal to, instead of ZL, we put the value of RL plus JXL over RL plus JXL plus Z Thevenin, which is 500 plus J 500 times V Thevenin, which is 35.35 with the angle of negative 45. We need to solve this equation in order to find RL and XL. Okay, so we continue. We will have, we divide both sides by 35.35 over with the angle of negative 45. So negative 45. So we will have 10 with the angle of negative 90 over 35.35 with the angle of negative 45 times RL plus JXL plus 500 plus J500 is equal to RL plus JXL. What did I do? I just simply divide both sides by 35.35 with the angle of negative 45 and multiply both sides by denominator. So we will have this equation. Now that we reached to this point, let's just see what is 10 with the angle of negative 90 over 35 with the angle of negative 45. It should be 0.28 with the angle of negative 45, or it's equal to 0.2 minus j.2. Now that we have this value, let's just write it down here. So 0.2 minus j.2 times RL plus JXL plus 500 plus J500 is equal to RL plus JXL. Now that we reach to this point, let's just multiply these two parentheses together and see what we have. If we multiply these two parentheses together, we will have a 0.2 RL plus J.2 XL plus 100, 500 times 0.2 is 100 plus J100 minus J.2 RL plus minus J.2 XL minus J100 minus J100 is equal to RL plus JXL. Okay. We know that JJ is equal to negative 1. Okay. So, or J squared. So, instead of this value, we put 0.2 XL, and instead of this value, we can put simply positive 100. Okay. And then what else we have? This term will be cancelled by this term. And if we simplify this equation, we will have 200 minus 0.8 RL minus J.2 RL plus 0.2 XL minus J.8 XL is equal to 0. So let's factor out or separate the real part and imaginary part of this equation. The real part is 200 minus 0.8 RL plus 0.2 XL minus factor out from J minus J 0.2 RL plus 0.8 XL is equal to 0. Because this term is equal to 0 in this equation, and it's a complex number, both the real part and imaginary part should be equal to 0. So we can say, in order to have this complex number equal to 0, we should have both real part and imaginary part equal to 0. So if we do that, we will have 0.8 RL minus 0.2 XL should be equal to 200, and point 2 RL plus point 0.8 XL should be equal to 0. If we solve these two equations, we will have RL is equal to 235.3 ohms, and XL is equal to negative 58.8 ohm. So as a result, we can say ZL is equal to RL plus JXL, which is equal to 235.3 minus J 58.8. So this one is the ZL. So the ZL is equal to resistor and a capacitor. The resistor with the value of 235.3 ohms, and the capacitor with the ZC equal to negative J 58.8. So this one is the ZL. In order to have in order to have 10 volts with the angle of negative 90 accuracy. Okay, so let's move to the next example. In this example use Thevenin theorem to find the current Ix in the following bridge circuit. Here is the circuit. We have a voltage source 75 with the angle of 0. We have resistor, we have capacitor, we have another resistor, we have one more resistor here, which is connected to the voltage source, and in the middle we have an inductor. The values is 30 ohm, 50 ohm, 60 ohms, negative J 120 ohms, and J 200 ohms. And we want to find find the current Ix in this circuit, which is the current moving through the inductor. So because we want to find the current going through inductor using Thevenin theorem, we need to consider this inductor as a load and find the Thevenin equivalent seen by this inductor, and then solve the circuit. So in order to do that, what we need to do, we simply need to identify nodes. We have node A here, node B here, node C here, and node D here, or like the reference point. Um, and what else we need to do? Let's just do not put the reference point for now. And we remove the inductor from the circuit and see what we will have. Let's just remove it. So we will have the voltage source. We have two resistors here, one resistor here, one capacitor here, which is connected to the voltage source, and point A and point B. Okay, the same like nodes that we put here. So we want to find the V Thevenin and Z Thevenin seen from these 2 points. So V Thevenin and Z Thevenin seen from A and B. So how we can do that? Let's just redraw the circuit in a different way, which makes it easier to like understand the connection between the circuits. So if we redraw this circuit, we will have point A here, which is connected to 30 ohm resistor, which is connected to negative J120, 50 ohm resistor, 60 ohms resistor. Here is point B, and in fact the voltage source is here, which we like show it in this way. Okay, so we can do that, of course, because there are just wires which connected the voltage source, and we move the voltage source in this location. The important like point is we don't change the connections. So the voltage source is connected to points C and D. Now we want to find Z Thevenin and V Thevenin seen from these 2 points, from point A and point B. Okay, first let's find the Z Thevenin. In order to find the Z Thevenin, we need to turn off the voltage source. So if we turn off the voltage source, we will have this circuit. Okay. And points A and B. So let's make it easier. So these two are in parallel, these two are in parallel. So we divide in this way. Okay, 50, 60, 30, negative J120. It's B. And of course points C and D are here because C was here, D was here, but they're short circuited to each other, so they are single node. And so here now it's easy. We can say the Z Thevenin is equal to 30 in parallel with negative J100 plus 50 in parallel with 60. Okay, which is equal to 29.1 with the angle of negative 14 plus 30, which is equal to 58.7 . angle of negative 6.9. So this one is Z Thevenin. Okay, we got Z Thevenin. Let's go back and find V Thevenin. So in order to find V Thevenin, we need to keep the voltage source on. So here we solve this circuit to find V Thevenin. Point A, 30, negative J120, 50, 60. We have the voltage source here, plus minus 75 with the angle of 0, and point A, point B, point C, point D. And now we can connect point D to the ground because we want to find V Thevenin. And let's see. Um, Here, if we draw the circuit in this way, let's have point A here, point C here, and point B here. From point A, we have a capacitor connected to the ground with a value of negative J120. Point A is connected to point C with the resistor of 30. Point C is connected to the ground with the value with the voltage source of 75 with the angle of 0. Point C is connected to point DB with the resistor with a value of 50, and point B is connected to the reference point with the resistor with a value of 60 ohm. And we want to find the voltage difference V Thevenin, which is the V Thevenin, which is voltage difference between A and B. So which is equal to VA minus VB. So we need to find VA, VB, and like subtract them to have V Thevenin, because we know that Thevenin voltage is the voltage across VA and VB. So now that we reach to this point, let's write the equations. The total currents leaving the node are equal to total currents entering the node. In order to write the currents leaving the nodes like this and this, we know that current is the the source node voltage minus destination node voltage over the impedance. So we can simply say VA minus 0 over negative J120 plus VA minus VC over 30 is equal to 0. The second one, this one is node A. Node B, we can say VB minus 0 over 60 plus VB minus VC over 50 is equal to 0. Point C. If we look to node C, we see that node C is connected to a voltage source directly, which the other side of the voltage source also is connected to the ground. So we can simply say VC is equal to 75 with the angle of 0. So we can just solve it in two ways. We can substitute VC in these two equations and find and solve two equations, two variables, or we can just solve it as is, like three equations, three variables, both are same. So let me just solve it in this way. First, let's factor, just rearrange these equations and factor out nodes voltages. So we will have negative 1 over J 120 plus 1 over 30 VA minus 1 over 30 VC is equal to 0. 1 over 60 plus 1 over 50 VB minus 1 over 50 VC is 0, and VC of course is equal to 75 with the angle of 0. Let's put these values in the matrix, and we will have negative 1 over J 120 plus 1 over 30, 0, negative 1 over 30, 0, 1 over 60 plus 1 over 50, negative 1 over 50, 0, 0, 1, multiplied by VA, VB, VC is equal to 0, 0, 75 with the angle of 0, and as a result VA, VB, VC are equal to 72.8 with the angle of negative 14, 40.9 with the angle of 0, 75 with the angle of 0. As I mentioned, V Thevenin is equal to VA minus VB. VA of course is 72.8 with the angle of negative 14 minus VB is 40.9 with the angle of 0 is equal to, okay, we need to convert them to rectangular form and then subtract them and convert back to the polar mode. I want you to pause the video and try to do this calculation and compare your answer with my answer. Okay, now that you calculated the Thevenin, I hope that all of you got this value, which is equal to 34.5 with the angle of negative 30.7 volt. If you got different value, just double check your solution to see what was wrong in the solution. And finally, we got V Thevenin and Z Thevenin. So let's just bring back the circuit in the form of Thevenin equivalent. So if we say Z Thevenin is equal to 58.7 with the angle of negative 6.9, and V Thevenin is equal to 34.5 with the angle of negative 30.7. This one is the equivalent of the circuit from points A and B, and now it's time to add the inductor. And Ix of course is the voltage moving through this inductor, and the value of the inductor, we know that it's J200. In order to find Ix, we simply use Ohm's law. The current is the voltage divided by the impedances. So 58.7 with the angle of negative 6.9 plus J200. Again, pause the video and calculate this value and compare it with my result. Okay, I hope that all of you got the answer of point 17 with the angle of negative 1.4 amp. So this one is the answer. Okay, so this one was the second example for Norton and Thevenin equivalent. Let's move to the third example for today. Third example. Okay, part A. Part A. Find Thevenin equivalent seen by inductor. Part B. Use Thevenin equivalent to calculate the current Ix. Okay, so the circuit is here. We have a current source, the value of 0.1 with the angle of negative 90, 100 ohms resistor, J75 ohm inductor, negative J100 capacitor, 10 ohms resistor, and of course the voltage source with a value of 20 with the angle of 45. Okay, and we want to find first the Thevenin equivalent seen by inductor, and find the current Ix, which is also the voltage going through the inductor. So the first thing first, we need to, in order to find Thevenin equivalent, we need to calculate, find the Z Thevenin and V Thevenin. First is finding Z Thevenin. In order to find the Z Thevenin seen by the inductor, we need to move the inductor and look to the circuit from these 2 points. Let's call them A and B. From A and B, and to see what's the equivalent impedance. So we will have this circuit. First, we want to find Z Thevenin. In order to find Z Thevenin, we turn off all the circuits and all the sources and find. So if we turn off the current source, it's open circuit. It's 100. Here is point A. Here is point B. Point B is connected to negative J100, and it's connected like this. And we want to find something is missing here. Yeah, this 10 ohm resistor. Okay, and we want to find the impedance seen from these 2 points. So if we read about this circuit in this form, it's A 100 negative J 100 and 10, and it's point B. So Z Thevenin is equal to 10 in parallel with negative J100 plus 100. If we calculate this value, it's equal to 1009.9 minus J.99. So this one is like the impedance of Thevenin equivalent. So for V Thevenin, we need to keep the voltage sources and current sources on and find the equivalent. So here is the circuit, point 1 with the angle of negative 90. We have 100 ohm resistor here. Here is 2 points A and B. So it's negative J 100, 10 plus minus 20 with the angle of 45. Okay, and that's it. So if we want to find the voltage, Thevenin voltage, seen from these 2 points, let's redraw the circuit in a different form. So let's start from like in this way. Let's redraw the circuit in this form. Let's say here is point B, and we have negative J100, 10 plus minus 20 with the angle of 45, 100, negative 0.1 with the angle of negative 90, and here is point A, and V Thevenin is voltage difference between A and B. Okay, so let me just use a red pen to show you the connection. So here is here, okay, and this one is here, this one is here, this one is here, this one is here, and this one is here. Okay, you see, because I moved point A to the bottom, you see that the direction of the current source reversed because it's toward the point A. If you look to the original circuit, here you see that the current source, okay, the current source sending the current to point A, and here the same thing. Okay, so now that we reach to this point, we need to find the voltage difference between point A and B. What we need to do, let's just write 2 kVL. So 1 kVL is here, we call it I1. 1 kVL is here, we call it I2. And if we say the voltage at this point is V1 and the voltage at this point is V2, we need to find V1 and V2. Okay, so let's write the equations. Of course, I2 is equal to, because there is a current source, I2 is equal to 0.1 with the angle of negative 90. That's it. For I1, we need to use Ohm's law. I1 is the voltage, negative 20 with the angle of 45 over the total impedances, so 10 minus J100. Why I said negative 20, not 20? Because if you look to this circuit, we see that the current is exiting from the negative terminal of the voltage source. In order to have this one as a positive, we need to change the direction of the current, but the final answer doesn't change, it's same. So this one is equal to 0.1999 0.199 with the angle of negative 50.71. Okay, so we got the current, so we know that V Thevenin is equal to minus V1 minus V2, because V Thevenin is in this direction, V2 is positive in this direction, V1 is in this direction, so we say V Thevenin is minus V2 minus V1. So it's equal to minus V2 is V1, sorry, minus J100 times I1 plus 100 I2. So this one is minus V1 minus V2, and it's equal to negative 15.4 plus J 22.6, or we can say it's equal to 27 with the angle of 35, sorry, 27.35 with the angle of negative 124.3. Now that we got V Thevenin and Z Thevenin, let's draw the circuit. So this one is V Thevenin, this one is Z Thevenin, and this one is the inductor. The inductor value is J75, and of course the current moving through this inductor is Ix. And again, in order to find Ix, we can simply use Ohm's law. Ix is equal to V Thevenin, which is 27.35 with the angle of negative 124.3 over the total impedances, 109.9 minus J 0.99 plus J75. Okay, so we calculate this number, which is equal to 0.206 with the angle of negative 158. So this one is the equivalent for this circuit. Okay, and I think we have one more example for Thevenin and Norton equivalence. So here is the last example. find Thevenin equivalent circuit seen from A, B. Okay, so here is the circuit. This time we have a dependent sources as well. So here is dependent sources with the value of Vx, 1 millihenry, 1 microfarad, 10 plus minus Vs of t, which is equal to cosine of 10 to the power of 4t minus 30 degree and point A, point B, and let's say we have, for example, let's Z load here. So we want to find the equivalent seen from point A and B. Okay. Excuse me. Okay. So first we find Thevenin for this circuit. Thevenin. In order to find Thevenin, we read about the circuit and keep all sources, and of course we convert the values to the phasor form. Okay, I'm not going to convert them to show how to convert the values to the phasor because you know how to do that. So we will have Vx, we have J10, we converted 1 millihenry to phasor with the frequency of 10 to the power 4, so it results in J10 for the inductor. And one more thing I missed in our original circuit, I should say that Vx is the voltage across the resistor in this direction. Okay, I'm telling you, we need it for this dependent source. Okay, and what else we have? We have the capacitor with the value of negative J100, and it's plus minus Vx. We will have 10 ohms resistor, and the voltage source, which in phasor of course is 1 with the angle of negative 30 and with the frequency of 10,000. And we want to find Thevenin, which is the voltage seen from points A and B. Thevenin, and if we look to the circuit, we see that the voltage across the inductor, if we call it VL, we can see that Thevenin will be VL plus this voltage. Okay, let's do that. Let's find the answer. So we identify our loop meshes and write the loops. So Thevenin loop 1, loop 2. Loop 1, because there is a current source in loop 1, the I1 will be equal to the amount of the current source, which is Vx. Okay, so we can say I1 is equal to Vx. But what is Vx? If we look to the Vx, we see that Vx is the voltage across the voltage across the capacitor. So it's the current moving through the capacitor multiplied by the impedances. The current going through the capacitor like includes of two currents, I1 and I2, because because of the polarity, we say the current is equal to I1 minus I2, because I1 is entering from the positive terminal of the Vx and I2 is opposite, times the impedance, which is negative J100. Okay, so if we substitute this value instead of Vx, we will have I1 is equal to negative J100 times I1 minus I2, or we can say 1 plus J100 I1 minus J100 I2 is equal to 0. So this one is the first equation, and the second equation, which is loop 2, we can simply say negative J100. I'm just writing the KVL for loop 2. Negative J100 times I2 minus I1 plus 10 I2 is equal to negative 1 with the angle of negative 30, or we can say J100 I1 plus 10 minus J 1000 I2 is equal to negative 1 with the angle of negative 30. We can convert this negative 1 to 1 by adding 180, so it's 1 with like 150, I think. So if we put them in the matrix and solve it, we will have 1 plus J 100 negative J 100 J 100 10 minus J 100 I1 I2 is equal to 0 negative 1 with angle of negative 30. Okay, if we solve these matrices, we will have I1 I2 is equal to 0.11 with the angle of 151 and 0.11 with the angle of 150. So now that we got I1 and I2, I said that Thevenin is equal to, let's go back to the circuit, Thevenin is equal to the voltage across this inductor plus this voltage. The voltage across the inductor is I1 times J10. So we can write it I1 times J10 plus 1 with the angle of negative 30, which is the voltage source, which is equal to J10 I1 is 0.11 with the angle of 151 plus 1 with the angle of negative 30 So as a result, V Thevenin is equal to 1.5 with the angle of negative 77. So this one is V Thevenin. Now we want to find Z Thevenin. Z Thevenin, because we have a voltage, so a dependent voltage source, dependent source. In this circuit, we need to use a test voltage source. If you remember, we apply the test voltage source and find the current and divide the voltage by current, and it's called Z Thevenin. Let's do that. Let's redraw the circuit again. We will have this circuit again. Vx J10 negative J100 10. And by the way, we should know that we need to turn off all independent sources. So we turn off the current source. It's here. And Vx is the voltage across the capacitor. And we add, if we say this point is point A and point B, we cannot turn off the dependent voltage source. We need to keep it on. So we add a test voltage source with the V test equal to 1 volt, and we find I test. After we found I test, we can say Z Thevenin is equal to V test over I test. Okay, so we need to solve the circuit to find I test. In order to do that, we again identify loops I1, I2, I3. So these are the loops. So let's write the loop equations. Loop 1, I, as we did for V Thevenin, I1 is equal to Vx, and we know that Vx is equal to negative J100 I1 minus I2. So as a result, 1 plus J100 I1 minus J100 I2 is equal to 0. So this one is first equation. Loop 2. Loop 2, we just write the KVL for loop 2, which is simple. Negative J100 times I2 minus I1 plus 10 times I2 is equal to 0. If we factor out I1, I2, we will have J100 I1 plus 10 minus J100 I2 is equal to 0. This one is the second equation. Third equation is coming from loop 3. We can say J10 J10, let me zoom out, J10 times I3 minus I1 is equal to negative 1 with the angle of 0. That's it. So let's just put them in order. So negative J10 with the angle of, with the negative J10 I1 plus J10 I3 3 is equal to -1 with the angle of 0. Okay. Now that we have these three equations, let's put them in matrix. So 1 plus J100, negative J100, 0, J100, 10 minus J100, 0, negative J10, 0, J10 times I1, I2, I3 is equal to 0, 0, -1 with the angle of 0. If we solve this matrix multiplications, we will have I1, I2, I3 is equal to 0, 0, 0.1 with the angle of 90. Okay, let's go back to the circuit. We see that I test is equal to negative I3. Okay, they are in opposite directions. So we can say I test is equal to negative I3 is equal to negative 0.1 with the angle of 90. So that we got I test, we can simply say Z Thevenin is equal to V test over I test. V test is 1 with the angle of 0 and I test is negative 0.1 with the angle of 90. So it's equal to 10 with the angle of 90, or it's equal to J10. So this one is the Thevenin. So we can simply draw the circuit. So we will have V Thevenin is equal to 1.5 with angle of negative 77, and Z Thevenin, which is J10, and that's it. So this one is the circuit, and we should know that the Z Thevenin, because it's J10, it includes or consists of a single inductor with a value of J10. Okay, so we can simply convert entire this circuit to not this circuit, this circuit, two sources, one independent, one dependent, including one inductor, one capacitor, and two resistors. We can convert all of those circuits to like a single voltage source and a single inductor. Okay, so this one was the last example for Thevenin and Norton equivalent.